Okay, someone was asking something. Please repeat your
Sir,
question.
yes, sir. My question is, for example, you have shown that the straight line x plus y less than equals to 1, and you have shown that the black portion of the triangular section shows represent this straight line's equation, area of the straight line.
Okay,
Am I
then
correct? Yes. Now, you also have shown that the another equation x plus 2y less than equals to minus 1, and you have drawn the straight line, and you have shown the area by curve mark. So my question is that why this is not only the triangular portion area for follows the straight line area, why the entire section of the straight line area?
okay, I understood your question. Uh, Actually, when I considered this particular region, just a minute. When I considered this particular region for the straight line x plus y is equal to 1, uh, this particular region is getting bounded by the x-axis and y-axis from the sides, because I cannot move into the parts of the negative quadrants, because the variables x and y is greater than or equal to 0. So I have considered this triangular section only. But when I drew the uh, area, when I drew the region bounded by the green colored straight line, the straight line is itself on the negative side. So I am considering the entire region, but those entire regions which fall in the negative quadrants, like this part has come into the picture, then this part has come into the picture, and that part has come into the picture, all these will be nullified subsequently. We shall not consider them, to show you that the region is not actually, that the region of the straight line is actually the entire side. I let see my cursor movement, entire side of this. Okay, when I shall do the board work, you will understand in a better way. So the entire side of this particular straight line. But from that particular, from the next phase of the problem, what I will do, I will try to eliminate, I shall eliminate this part because it falls in the negative quadrant. I shall eliminate this part because it falls in the negative quadrant. I shall eliminate this part because it falls in the negative quadrant. I shall consider the part of the region only which falls in the positive side, and we will get to see. Just follow what I'm going to say to you in the next phase of the problem, and you will get your answer. But first of all, ensure that whatever so far whatever I've said to you, you have understood this particular point. Okay, first of all, you ensure that you have understood how I mark the regions. That is very important. Step number 2 is that that has already been discussed. It is after drawing all the straight lines, we mark all the regions. Okay, fine, that has been done. Step number 3 is after marking all the regions, we identify the common feasible region bounded by all the straight lines. And write the coordinates of all the corner points. Okay, anyways, let me explain this particular part to you. Forget about y equals to 3. That is that is a single straight line. It is actually not covering any region. We have to consider the points on the region only. So it is not having any common point with the points falling in the region of this portion or those portions. So it is separate. So that will be that shall not be considered. Why shall not be considered? I shall clarify gradually. But if I consider the first two equations, like the region bounded by the green colored portion and the region bounded by this x plus y equals to 1, you will see that some portion, if we extend the, if you draw this by a pencil, you will see that the portion will cut, the black portions also. This black portion, this triangular portion will be the common region, which is getting bounded by this green colored straight line as well as this particular straight line. I have shown a few curves over here, because if you extend the curves, you will see that they are also falling. The part of the region is also falling on this particular triangular portion also. So that is the common part. This triangular portion is the common part bounded by this straight line and that straight line. We shall only consider the common region bounded by all the straight lines, the common region bounded by all the straight lines falling on the positive side only. So we shall not consider this part, and that part, because in these parts, one of the variables becomes negative, and which should not be according to the linear programming problem. But we are not considering y equal to 3 because no part of the region, no part of this particular straight line, that means no points falling on the straight line is common with this region. So actually we can say that this constraint y equals to 3 is redundant constraint. Redundancy means something which can be avoided and which avoidance of which doesn't affect your solution. That is called redundancy. So y equal to 3, if you keep it, if you retain it or you omit it, it doesn't affect my solution according to the steps given for the graphical method. Okay, so in the graphical method, in step number 3, it is written, you are only going to consider the common region bounded by all the straight line. What do we mean by feasible? This is an important word. Feasible means bound the common region. Consider the common region bounded by the straight line, but keep in mind that all the parts are positive. That is the feasibility. If one of the variables becomes negative, then this is not feasible, it's infeasible. Okay, so we have to consider the feasible common region bounded by all the straight lines. In this case, that this particular section, this particular triangle is the common feasible region bounded by the straight line this and that. This is the redundant case. There may be in some instances of in linear programming problem that you may find that some variables get redundant or some equations get redundant. I can cite one example about redundancy. Suppose 4 of your friends are actually meeting in a pub and having party together and discussing among your friends that about your lifestyle. And suddenly a movie star joins you, okay? And he makes friendship with you and he joins your party and he also starts discussing about his lifestyle. Obviously, the movie star's lifestyle will not tally with your lifestyles. So he will be the redundant case, which can be avoided. Because his lifestyle can no way affect your lifestyle. So in such case, in a linear programming problem, such case may happen. That some equation may become redundant. You can avoid it. Okay? So we got our common feasible region in the shape of a triangle. And the triangle you have got, what was written over there? Mark your common feasible region and mark the corner points. So you see, corner points are those points where the line change its direction. So anybody can say that there are 3 corner points in the triangle. You can say the vertices. Okay, this will be the more appropriate word. So we have 3 vertices for this common feasible region. One vertices is the origin itself, another vertex is the point 1, 0, and another vertex is the point 0, 1. So we have got our vertices only. Step 4 is telling you, oh, there is another line is written. In the above problem, the common feasible region is the shaded triangle OAB. The corner points are respectively the origin itself, the point A01, the point B10. Okay, and after you mark your corner points, step number 4 says that one after another, subsequently, you put the coordinates of the corner point in the objective function. That means you find the value of z at the point 0, 0. You find the value of z at the point 0, 1. You find the value of z at the point 1, 0. So when we find the value of z at the point 0, 0, that means we are putting x equal to 0 and y equal to 0. The value is b0. When we find the value of z at the point 0, 1, we are putting x equal to 0 and y equal to 1. And this becomes 2 into 0 plus 3 into 1, that is 3. And the third is z equal to the value of z at the point 1 0. So we are putting x equal to 1 and 2 equal 3, y equals to 0. So we are getting 2 into 1 plus 3 into 0, the value is 2. So we have got 3 possible values for z. Step number 5 is saying draw conclusion by analyzing at which point or points. There may be several points. Maybe that means for 2 different values you may get the same value for z. Okay, it may happen also. So draw your conclusion by analyzing at which point or points the function is either maximized or minimized. That means out of all the values you have got for the objective function z, if it is a problem of maximization, find the maximum value. If it is a problem of minimization, find the minimum value, and your job is done. So in our case, the problem was of maximization type, because you have been asked to maximize z, and you see that out of among these 3 values 0, 3, 2, the maximum is 3. And so the objective function, the objective function has been maximized to 3 units, and it is occurring for the point a01, that is for the value x equal to 0 and y equals to 1. So x equal to 0 and y equals to 1 becomes your solution, your optimal solution to the given problem. You may ask me one question at this juncture, that sir, actually we know that a region, this particular portion, common feasible region, contains infinitely many points. Okay, so because in a 2-dimensional, we are actually considered a 2-dimensional plot, and this 2-dimensional figure, this region contains infinitely many points. So why are we considering the corner points only? Because of a theorem. The theorem says that if we consider a common feasible region, then corner points will give you the optimal result. The proof of the theorem is not there in the syllabus, but you have to memorize the theorem. The theorem says if we have a common feasible region, the corner point will define the optimal solution. At one of the corner points, you are going to get your optimal solution. So this is all about graphical method. The first of all, the step number, I'm recapitulating. First of all, you have to bring the equation in the intercept form and draw the straight lines. If the transformation to intercept form is not needed, you don't have to do it. You draw all the straight lines in a common graph. This may be a graph paper, or this may be a white sheet. After you draw the graph, you can, applying the rules, you can mark the regions. After marking all the regions, if there are any redundancy, you remove. If there is no redundancy, you retain. Mark the common feasible region bounded by all the straight lines. Mark the corner points and their coordinates. Put the value of the coordinates in the objective function, and out of these values, different values of the objective function, if it is a problem of maximization, find the maximum value. If it is a problem of minimization, find the minimum value. And your job is done. Your graphical method is done. So this is the methodology of graphical method. I am going to now stop the share, and I am going to go to the whiteboard. I'm going to share a whiteboard with you to show you some other problems, some other graphs, and the things will be more clear to you. Okay, so after this, you just see what is happening, what I'm showing you. After that, after this session ends, we will again enter into the new session, and there you can ask me your doubts. I shall try to give answer to your questions over there. So here is the whiteboard I'm sharing. Probably you are seeing this. So let me consider a problem. Okay, from my mind. Okay, so suppose I am going to, suppose I'm going to consider this particular problem. The problem is mean z is equal to x plus y. x minus y. Okay, the mean z equal to x minus y, and it is subject to x plus y is equal to, sorry, greater than or equal to uh, three. That is one equation. And next I'm considering 2x plus 2y less than or equal to 4. Okay, and x comma y greater than or equal to 0. This is my problem. I am going to solve this problem graphically. This is my problem. Okay, I am going to solve it graphically. Now I'm going to draw the graph in front of you, and the thing will be clearer. Okay, so just don't worry, concentrate. First of all, let me go to the next page. This is the question page. So my question is this one. This is my problem. Okay, let me go to the next page. First of all, I shall identify the constraints given. I shall try to draw the constraints. Your step number 1 is to draw the axis, x-axis or y-axis. So let me draw the x-axis or y-axis first of all. So this is your y-axis, and this is your x-axis. You see, this is the step number 1. Okay, and let me mark the names over here. In the note there was a mistake, so this should be your x and that should be your y. Fine. What is needed? And I am only considering the positive side, and this is the origin. You know, actually other quadrants are also there, because if we draw two straight lines like this, one cutting horizontally, the other vertical, then it actually divides the entire page into four different parts. This is called the first quadrant, that is called the second quadrant, this is called the third, and this is called the fourth. For the non-negativity constraints, I shall consider only the first quadrant. All the entire problem will be done on this particular quadrant, and it is a very positive sign, because we are not very much comfortable with negative numbers. My next job is to draw the straight lines. What is the first straight line? It is x plus y greater than or equal to 3. Okay, let me write the straight line first. What is the straight line? Straight line is x plus y is equal to 3. Greater than equal to 3 is the inequation. It represents a region. But what is the straight line? Straight line is this one. Is this straight line in its intercept form? No. Because in the intercept form, on the right hand side, we need to have 1. So let us bring this in its intercept form. So this implies I shall divide both the sides by 3. So x by 3 plus y by 3, I hope now you are enjoying, is equal to 3 by 3, that is 1. I have got my intercept. So x intercept is 3 and y intercept is 3. So let us mark the point over here. So suppose this is, you can do it arbitrarily, or you can take the help of scale. Okay, we are not children, we can do it easily. So this is my point 1 on the x-axis, this is my point 2 on the y-axis, and this is my point 3 on the this is my point 2 on the x-axis, and this is my point 3 on the y-axis. Sorry, x-axis. We don't have to consider other points, because you see 3 is there. Our job will be done by that. Similarly, you consider y-intercept is also 3. So you consider a point 1 in the y-axis, point 2 on the y-axis, and point 3 on the y-axis. What is the intercept what is the intercept form of the straight line? X by 3 plus y by 3 equals to 1. So what we do, we join the two intercepts, one in the x-axis and another in the y-axis, and let me join them. So this is my straight line represented by x plus y equal to 3. We can name this straight line as this. Suppose this straight line is my line 1. Suppose this straight line is my line 1. One straight line has been drawn. What is the other straight line? Let me draw it now. The other straight line is 2x plus 2y less than or equal to 4. Okay, so let me write it. Write the straight line. 2x plus 2y is equal to 4. That is the straight line. Is it in its intercept form? The answer is no. It is not also in its intercept form. So let me bring it in its intercept form. We shall divide both the side by 4. So I'm writing it as 2x by 4 plus 2y by 4 is equal to 1. And we can simplify this as x by 2, because 2 cancels 4, x by 2, y by 2 is equal to 1, because 4 is divided by 2, and the answer is 2. So we get this after the simplification. So what we get a straight line in its intercept form, x by 2 plus y by 2 equals to 1. So now the intercept is this one. This is the x-intercept and this is the y-intercept. Okay, for the second straight line, let us name this straight line as line 2. Now we are going to join them. So I am joining this straight line. Just a minute. Can I select a different color? That would be great if I can.
Yes, sir. Yes, sir.
Yeah. Okay. Then this is the straight line. So one straight line, this black straight line is line 1, and the blue straight line is the line 2. Okay. Now, after drawing the curve, after drawing the straight lines, we are not interested about the straight line. We are interested about the region. So we shall consider, now we shall consider the actual equation, what we have got. The actual equation is, x by 3 plus y by 3 less than or equal to 1. This was the actual inequation which I have got. You put x equal to 0 over here, and you put x equal to, just a minute. Oh, sorry. This was not less than or equal to, this was greater than or equal to. So greater than or equal to 3, greater than or equal to 1. Okay. So you put x equal to 0 here and y equal to 0 here. And we get 0 by 3 plus 0 by 3, that is 0, which is greater than 1. And this is absurd. If we substitute 0, then if we substitute 0 in place of 0, 0 in place of x and y, this becomes, the inequation become absurd. Therefore, the origin is not actually satisfying this inequation. And according to the rule given in the PDF, I told you, if the origin doesn't satisfy the inequation, you have to consider that side of the straight line. You have to consider that side of the straight line which doesn't contain 0, 0. If the origin means 0, 0 doesn't satisfy the inequation, we have to consider that side of the straight line which doesn't contain 0, 0. So for line 1, that means this black line, your region will be this one. This will be your region. Just a minute. This side will be your region. How can I draw it? Let me try to draw the region properly. Just a minute. This side, these sides of the straight line will be the region. So I'm marking them like this. The entire side on this half will be the region. And if I consider the second line, if I consider the second line, that means this one, what was the actual inequation? The actual inequation was 2x plus 2y less than or equal to 4. So you see, let me write the actual inequation. Actually, inequation we have got is this one. X by 2 plus y by 2 less than or equal to 1. Now, if you substitute x equal to 0 and y equal to 0 over here, then you see 0 by 2 plus 0 by 2 is less than or equal to 1, which is actually satisfying the inequation. And according to that rule, it is said that if it satisfies the inequation, then the region bounded by the straight line will be that side which contains the origin. So in this particular case, the region will be this. This side will be the region. This side will be the region. The entire half will be the region. Everything inside this triangle. This will be the region for this line 2. But you cannot cross the barriers marked by this portion of the y-axis and that portion of the x-axis. It's because the variables x and y cannot be negative. And this side is also positive. Okay, only consider the positive part of the side. So for the two lines we have got, two regions. One region is on that side, and another region is on this side. One region on the side above the straight line 1, and the second region is below the straight line 2. What was written in the note? In the note it was written that after marking the region, you are going to find the common feasible region. Common feasible region. The region bounded common feasible region means the variables here are all positive, non-negative, and the region is the common part of the region which is bounded by all the straight lines. Okay, so you have to mark them. But here, carefully you observe, you have got a mutually exclusive kind of region here. Totally disjoint region. This red side corresponding to the line 1 is no way common to the green side corresponding to the line 2. And therefore, this particular problem has no common feasible region. This particular side is, pardon my handwriting because I'm using my finger. This particular problem doesn't have any common feasible region. But what graphical method said? Graphical method said that to find the solution, to optimize the thing, you need to get a common feasible region. After getting the common feasible region, we mark the corner point and do whatever, such and such things. But if a particular problem doesn't have any corner point at all, our conclusion in this case would be this is conclusion actually, sorry. Our conclusion would be this particular problem has no solution at all. This particular problem has no solution at all. Or you can say that this particular problem has infeasible solution. No solution or infeasible solution. Okay, so this is another type of problem. Graphical, but its solution is different from the earlier one. In the earlier case, you got a feasible solution, a unique feasible solution. Now you have got a solution which is infeasible. Okay, let's do another one. I shall consider now the same problem, but I will change the sign and let's see what happens. Okay, if I discuss on the same, if I consider the same problem, then it will be much better for you to understand. Okay, so what is happening over here? So let me consider the problem 2. Sorry, let me go to the next page, next new page, and the problem is say min z, same object. I'm not going to change the objective function. It is min z is equal to x minus y, and subject to x plus y greater than or equal to 3, and 2x plus 2y greater than or equal to 4. Previously, I considered less than or equal to 4. Now I am considering greater than or equal to 4, and non-negativity constraint x comma y greater than or equal to 0. One thing probably you have noted down that in the linear programming calculation, the unit of the variable is not important. Only the equations and the variables in itself is important. Okay, so let us quickly solve it. So we shall let me do this in this particular page so that you can understand. You have already got its the main essence of the structure. So now let me quickly draw the x-axis. First of all, this is my y-axis and this is my x-axis, and let me name them for better clarity. So this is your x, this is your x, and sorry, and this is your y-axis. And now I'm going to draw the straight lines. We already know the points. We have already known the intercept form of the straight lines, so we are not going to repeat them. So this is my intercepts. These are my points on the x-axis, 1, 2, 3, and these are my points on the y-axis, 1, 2, and 3. My first equation was x plus y is equal to 3. So let us draw it. So my first equation is this one, and my second equation is x by 2 plus y by 2, x by 2 plus y by 2 greater than or equal to 1. So that was my second equation. Okay, sorry, what happened? Just a minute. This is my second equation. Okay, now you see, if I substitute 0, 0 in this particular equation, so 0, 0 was not previously satisfying the equation. So we already know what particular part of the region will be bounded by this particular equation. That part is this one. This is the part. But here the scenario has changed. In the second one also, if you put 0, 0 now, 0, 0 greater than 0 plus 0 greater than, it becomes greater than 4. So 0 becomes greater than 4, which is also absurd. So now this particular straight line will contain that side of the region which doesn't contain 0, 0. So previously this was the side which was bounded by the straight line, previous straight line. Now this side will not be taken into consideration. I shall consider rather these sides. Okay, these are the sides I shall consider. And you see, you can now identify the common part bounded by all the straight lines. The green colored portion has got mingled itself with the red colored portion, and therefore the common feasible region is this part. The common feasible region is this entire part lying on the right hand side of the blue colored straight line. Okay, Since it is a minimization type of problem, so we shall mark the corner points. Here are the corner points for you. This is one corner point and that is another corner point. These are the lowest points of the boundary. Okay, and what are the coordinates of this corner point? This corner point has got coordinate 0, 3. Sorry, this corner point has got coordinate 0, 3, and that corner point has got coordinate 3, 0. Fine. And if I substitute the values over here in this section, you see, just a minute. If I substitute this, you will get z is equal to, put x equal to 0 and y equal to 3, you will get z is equal to minus 3. And if I substitute z, the point 30 over here, you will get z is equal to, put x equal to 3 and y equal to 0, you will get 3 minus 0, that is, we will get 3 minus 0, that is 3. Since it is a minimization type of problem, which of these two is the minimum value? This is the minimum value, and your answer is 0, 3. 0, 3 is your optimal solution to the given problem. But there is a beautiful thing which I must share with you. The beautiful thing is that if I change this particular problem to maximization type, if we consider the problem now as max z is equal to x minus y, if I change this mean problem to max problem and keep the constraints as it is, I'm not changing the constraints. So the scenario will be the same. The common feasible region will be the same. Okay, but since the problem has now become maximization type, then you cannot say that 0, 3 or 3, 0, they will be the answer to the they will be the solution to the given problem, because they are the lowest point. So for these same constraints, if the problem is of maximization type, you can easily see that if we keep on increasing the values of x and y to say unboundedly, then your objective function will keep on increasing, and it will keep on getting maximized and maximized if you keep on increasing the values of x and y. Okay, so in that case, in this scenario, we shall conclude that the given problem has unbounded solution. So the same problem is actually changing its shape uh, depending upon what objective function you have and what constraints you have. So constraints and objective function, they affect the problem very much. I am again repeating, for the problem is what the problem was actually of minimization type, so we got some minimum values corresponding to the corner point because this define the minimum values. But if we retain the constraints as they are, and if we change the objective function from minimization to maximization, the same problem has got a different solution, and that is unbounded. And the previous case, there was no common feasible region corresponding to the constraints given. So the answer to the problem was the problem has no solution or has infeasible solution. Now I have less than 1 minute. It is going to get cancelled. After that you join, and then it becomes a question answer session where you can put your question and I'll try to give the answers accordingly. So let us just wait for the class to be cancelled. Okay, then we shall start.